Welcome back to Introduction to Material Science and Engineering. We are still in Chapter 7 of the Callister text, which is Mechanical Properties, and this is our second lecture. Our last lecture on mechanical properties dealt with elastic properties of materials, and now we are moving beyond elasticity into plastic deformation and yield. So if we go back to our handy uniaxial tensile bar that we started with at the very beginning of the elasticity section, and we apply that same load per unit area, which would be our sigma normal tensile stress, and we deform an increment d just like we did before, we'll see that once again our interatomic average spacing goes beyond equilibrium. Bonds stretch effectively, as is shown over in the left-handmost diagram. But if we continue to apply larger loads, as shown by the big bold F in the center diagram, we can induce a little bit more deformation, in fact quite a bit more deformation, and that's indicated by the bottom D plastic in the center diagram. At this point, we'll notice if we zoom in on our atomic structure again that we've now done something different. We haven't just pulled the planes of atoms a bit more apart, increased interatomic spacing, we've actually caused them to slide relative to one another. So not only are the bonds stretched, but we've actually had some shearing. And what happened here is we started to move dislocations. So we had those edge and screw dislocations moving over, and as we noted back in our section on defects, once a dislocation moves, the material deformation is not reversible after we release the stress. And that's what we see in the rightmost section, that we take that bar that we had applied a small and then a larger load to, and we release all the loads. We recover the original D deformation, which of course corresponds to elastic deformation, but we retain the plastic. It is irreversible. And you can see that if we looked on the atomic level, the space between the stretched planes of atoms has disappeared again, and that's our elastic strain, but that slippage between planes, that sideways shear indicated by the diagonal lines, is still there. So that's representing the shearing, which can be related to also a tensile deformation as a result of dislocation movement. So we can see that depending on the load, we can actually have two different types of deformation: the reversible elastic and then the irreversible plastic due to dislocation movement. Okay, so how do we measure that? What can we see if we do a stress strain test with our handy dandy load frame and load cells, next tensometers? So if we put a sample in our load frame and we started applying more and more stress or applying more displacement, we would initially see our linear elastic regime shown there in the pink, and we could stress it, release the load, and we would move back and forth on that line, and we would be pulling the atomic planes apart. But once we got to the point where we could start moving quite a few dislocations, we would start getting our plastic strain, our permanent deformation, and we would notice that we would lessen the slope of our stress strain curve. We would get it healing over. So for every new increment of stress, we get a little bit less strain. So the curve flattens a bit. But the strain that we get is not recovered when we reduce the load. This type of behavior applies to metals, especially at what we call low temperatures. This doesn't mean cryogenic temperatures, but it means temperatures that are generally less than 1/3 of T melt. That's a good benchmark number to think about, because if we go over that, we start to get viscoelastic behavior even in metals. Polymers will display viscoelastic behavior even at room temperature sometimes, which might be a significant fraction of their melting point. But if we're looking at a metal, generally if we're at 1/3 of the melting temperature or less, this is the type of behavior we see. And for most ordinary structural applications, we're working on or around room temperature, so that's just fine. Now, if we release the load, remember, we do recover the elastic portion of the strain. So if we got to the point of highest load and then turned the load frame off, released all of the loads, the sample would contract back along a line on our stress strain plot that is parallel to the original slope of the elastic portion. And then the permanent plastic deformation could be read off of the strain axis at the last point where it says permanent plastic after load is removed. So if we have small plastic strains and large elastic strains, we need to remember that the total strain right at the time of max loading is a combination of two different types of strains. And if they were, say, measuring the sample length after deformation, we're only measuring the plastic. If we go all the way to failure on fairly ductile materials, the plastic elongation will generally swamp out the elastic. It's much, much greater. But for more brittle materials, it can be the reverse. So we just need to remember that as we load a material, if it's still under load, we've got a combination of the two strains. So you can see E plastic is not the full strain at failure. It's the strain after we subtract back the elastic portion. Okay. So if we've gathered some cool stress strain data from our uniaxial tensile machine, we've got our test data, how do we start calling off these important properties like yield stress and yield strain that we might want to, say, compare another material to or report out on our product literature if we're designing a new material? So we're going to define a term called the 0.2% offset yield. This is not used for every material, but it's fairly general. It's included in a lot of the ASTM tests for metals and more rigid polymer uniaxial tensile tests. If you see a specification noting a yield stress or a yield strain, if it's not otherwise noted, chances are it's referring to the 0.2% offset. So, okay, what does this mean? It means that you define the yield stress and strain by the strain, in this case, that represents 0.02% starting from zero. When we trace back our elastic strain parallel to the original loading curve. So just what we show on the diagram. So we would start at the origin, go over 0.002, and since strain is otherwise dimensionless, that's elastic strain, it's 0.002 unitless, and then draw a line parallel to our original stress strain curve, using the slope equal to our modulus, and to where it intersects our actual measured curve. And that point at which we intersect our actual measured stress strain curve with our constructed curve is the yield stress. So we just need to practice that a little bit to get the gist of it. The important thing to remember is to measure over that 0.002 and to not draw a line vertical from that point, but to draw it parallel to the elastic portion of your measured curve. So you're gonna draw it with the modulus slope included. The biggest mistake a lot of people make is to go over 0.002 and then draw a vertical line straight up to hit their measured stress strain curve, and of course that will underestimate the yield stress. So we go over 0.002 strain for the 0.2% offset, and then we draw up parallel to the elastic regime, and where we hit the measured curve is the defined 0.2% offset yield stress. So how do you use it? If somebody says, your strain is 0.002, how would that correspond to actual displacement if you were measuring it on a sample? For example, if a 2-inch long sample, what would a 0.002% strain correspond to in terms of actual measured displacement? So what we would be measuring on our extensometer, that would again be our definition of strain. So delta z over z, which would be z naught in this case, that we're showing over in the example equation on the lower right hand side of the slide. If we were given a strain of 0.002 and someone wanted to say, well, what was the extensometer on our tensile test measuring at that point? What's our delta L? We would just measure the original sample length of 2 inches, multiply it by 0.002, and we'd get our delta L of 0.004 in this case. So that would be the extensometer delta L, or in this case delta Z reading, corresponding to a 0.2% strain for an original 2-inch length sample. So pretty much just the definition of strain there. Okay. How does yield compare across material categories? A little bit more spread in metals now. You can see this just shows, in fact, there's some that have higher yield stresses, but steel, if it's quenched and tempered, a heat treatable steel like 4140, it's pretty high, getting up into the well above 1,000 megapascals, and again that's 10 to the 6. So we're seeing a different order of magnitude versus what we saw with elastic modulus. Now we're reporting sigma y in megapascals, so that's 10 to the 6 as opposed to gigapascals, 10 to the ninth. Going but a bigger range for metals, so we go above 1,000 to about 50. Aluminum has a much lower yield, and again that's annealed aluminum. You can see the effect of processing. You can see a few of these materials in the annealed state having a much lower yield than in a heat-treated state or a cold work state. So that's one of the main goals of heat treatment and mechanical processing for metals, is to increase yield. In some cases you'll also increase tensile, but typically we design around yield. We don't like things to bend in service unless it's a deliberate processing method. So although we need to be cognizant of tensile, we typically design for yield. Ceramics, graphite, semiconductors, quite often yield strength isn't defined because they will break in the elastic regime. They don't have much in the way of fracture toughness, and like we discussed in terms of dislocations and it being easier to create a surface in order to displace the material if you don't have dislocations, when we were discussing the essential role of dislocations in ductility and material deformation. In the case of ceramics, semiconductors, graphite, it is so hard to move a dislocation in those materials. Their bonds are so strong that even with the higher energy and limited number of atoms that need to be moved to move a dislocation, it's nonetheless still sometimes easier to create a surface, and so they fracture before they can move their own dislocations, and so they're elastic only materials, very brittle. Polymers, lower spread in yield strength, but also much lower in general compared to metals. And composites and fibers, again, if you have a rigid matrix, they're going to behave a bit like ceramics and fracture, and their yields are less well defined. They're typically defined just simply by ultimate tensile strength. Okay, what happens when we go beyond yield? What if we're planning for a forming operation or something where the plastic deformation really matters? May not matter in a lot of service applications, but it's certainly important if we're going to form, because most of our material behavior will be deliberate yielding. We might be designing a process where we're actually deforming something. We're bending or rolling or pressing or what have you. So this gives you an example of what a side view of a uniaxial tensile bar, a metal specifically, would look like if we put it into controlled displacement and we measured engineering stress over engineering strain. So starting at the left-hand side of the curve, we're going to load it up. It's going to deform elastically along a straight line whose slope is defined by the Young's modulus. At some point we're going to begin to yield. We're going to move dislocations in that material, and we're going to deviate from that steep straight line, and the stress strain curve is going to bend over. and then it's going to continue at a much, much lower but still increasing slope to point M. And that is known, that maximum point of tensile stress is known as the ultimate tensile strength, or just simply tensile strength. Now, if we're measuring engineering stress beyond that point, we can keep deforming it. We can keep applying more stress and continue to deform, but the curve will actually start to descend at this point, even though we're continuing, in most cases, to increase the load. And you're going, now wait a minute, how can the load be increasing but the stress is decreasing? Well, what's actually happening is we get what's called necking. We get a localized deformation where the average area doesn't really decrease that much, but in one local spot it decreases significantly. And so we may have a higher load per unit real area, but because we're ratioing that load to the original cross-section area to define engineering stress, it's actually less. So if you took the actual load per unit area in that neck, it might be significantly higher. But because engineering stress is defined as the load per original area, the curve actually goes down. But in that local area in the neck, the stress is continuing to go up, and we actually will continue to strain the material, continue to elongate it until it finally fractures. And so the fracture stress and the fracture strength is defined by that final point, in which case the load will drop completely back down to the x-axis. In this case, not necessarily returning along a path parallel to the modulus, because there is no longer anything to return it. So in this case, the neck acts as a stress concentrator. This is very important, not so much for this chapter, but it will be very important for fracture, because the minute it forms, the area in that neck is no longer really being subjected to stress just from one direction. So it went from having stress just in, say, the vertical, the z direction. Now it has an x and y component, and it has what's called a triaxial stress state, much more prone to fracture. So the test is no longer uniaxial per se beyond ultimate tensile strength. So the behavior beyond that is less easy to interpret, but it can still give us an idea of how ductile the material is and how tough it is. So we define our fracture characteristics on a stress strain curve all the way out to fracture, but we specify our tensile strength as merely the highest point. Okay, tensile strength comparison. So these are basically the same materials. You can see that in the case of metals, the tensile strengths are a little higher than yield. So anytime that happens, going back a slide, our yield stress would be, from this diagram, maybe 25% lower than our tensile stress. So we continue to make the material stronger between the time that we yielded and the time we reached the maximum engineering stress, and that's known as work hardening, and we'll talk more about that in chapter 8. It's a means of material strengthening that basically involves creating more dislocations in a material and tangling them all up so that they cannot move easily. And if a dislocation cannot move, a material cannot deform, and the yield strength goes up. So that's what's happening continuously in our test sample as we continue to strain it more and more, force it to elongate. And so we have about the same range of tensile strengths in our metals and alloys as we had yield strengths. Now that we're measuring ultimate tensile strength, we can get some numbers for our brittle materials. Again, they don't yield, they just load up in the elastic regime and then break. But we can certainly measure what the max load and per unit area that they could carry before break. And you can see that they're somewhat lower than metals, although there's a broad overlap. And again, they are overlapping ceramics on their bottom end with polymers, and composites are soup to nuts, with big changes with fiber reinforcement orientation and some with matrix. Ductility. So how far does something deform? How much strain do we get before we fracture? So ductility is literally defined as strain at failure. It has a verbal definition on this slide as plastic tensile strain at failure, but our percent elongation is defined by the length at failure, or the area, cross-sectional area at failure, minus the original length or cross-sectional area ratio to that original length or cross-sectional area. So a real good practical definition of ductility is literally engineering strain at failure. So if somebody says, I did a tensile test and I got a 50% strain at failure, what's the ductility? 50%. So it's really, really easy. So there's ductility defined on the upper right in terms of length change, and then in terms of area change. Toughness. So we're back to area under the curve. At the end of our section on elasticity, we defined resilience as being the area under the stress strain curve only in the elastic portion. So if we had a function for stress as a function of strain, we could take the integral of that from 0 up to the yield strain and measure the area, or calculate the area under the curve, and that would be resilience, or the mechanical energy absorbed by a material only due to elastic deformation. Well, now we know a material can deform with plastic deformation as well as elastic, so what about the energy that you absorb by plastic deformation, moving all those dislocations? Is that more? Is it less? Well, it depends on the material. So obviously, if you have a ceramic, a very brittle material that doesn't in fact undergo any plastic deformation, well, you're not going to have a lot of energy absorbed by deformation that doesn't happen. So those will actually have what's called a very low toughness, and in fact what toughness it has is only resilience. So it could be that the area under the curve, such as we see in the blue portion, the blue material on our graph that says small toughness ceramics, that could be pretty much all or nearly all elastic strain energy. A metal, especially one that hasn't been strengthened significantly, is going to have certainly a measurable resilience, a measurable elastic component to its area under the curve, or its mechanical energy absorption, but most of it is going to be coming from plastic deformation. And so that would be shown again by the difference in yield stress, yield strain, if we're integrating over strain, which actually overlaps with the blue dotted line representing the fracture strain for our ceramic material above it. But the triangular portion of our green stress strain plot area under that green stress strain plot would be the elastic energy absorption by our metal, and then the remainder, the much larger portion of the area under the curve, would be the energy associated with moving dislocations and plastic deformation. So the total area under the curve is known as toughness, and for a metal, most of it is coming from plastic deformation. An unreinforced polymer and many elastomers have tremendous strains at failure. They can elongate 200%, some of them 500%. But they're not very strong. Their tensile strengths are low. So that is what you see there on the red curve. That would be an unreinforced polymer, probably a fairly ductile one. And so its area under the curve is actually fairly low. So it doesn't have a very high toughness because it really, volume per volume, can't absorb that much energy, not because it can't deform, but because it can't hold much load with that deformation. So it's kind of like work. The definition of work is being forced through a distance. A ceramic can take a lot of force over a very small distance. An unreinforced polymer can move a tremendous distance but not carry much load. So it's literally just the area normalized version of work in this case. So again, the bottom catch-all line, brittle fracture is associated with elastic energy. When we start looking at the energy that drives cracks and stops cracks, if we can load up a lot of elastic strain energy in a material like we can in a ceramic, we have the capacity to hold energy in a material that can drive pre-existing flaws into cracks to failure. If the material can absorb energy plastically, it can literally blunt cracks, deform at the crack tip, and stop its own cracks. So that's one of the reasons why materials capable of plastic deformation of any kind have much, much greater toughness than ones that don't. Which brings us to ceramics. Why is it that ceramic materials are so much more brittle? From the first day of this class, you probably heard myself or another instructor talk about the dangers of designing with large, thick, monolithic ceramics and how they shouldn't be put in tension or in fracture critical applications. The reason that they don't have fracture toughness and why they can't deform plastically is dislocation movement is so very, very difficult. Ceramics are either ionic solids or they're covalently bonded solids, and in ionic solids, to move a dislocation, sooner or later you have to bring cations in close proximity with other cations, because an ionic lattice, of course, has alternating positive and negative charges. Usually the cations being, in the interstitial sites and the anions being on the lattice points, but a dislocation will eventually index everything over, and so you'll have like charges going into very close proximity. That has a very high repulsive force. So in order to get a dislocation movement to move, you have to overcome that force. And again, when the forces are that high, it may be easier to form a surface with the air, which means fracture. And the same with strong covalent bonds. Even though you're only moving a few of them right at the edge of the dislocation, nonetheless, it may be so hard to move those few bonds that it's easier to create a surface and fracture the material. So it's truly the strength of those bonds and the inability to move a dislocation that makes these materials so brittle. Metal bonds are strong, but because the electrons are delocalized, it's very, very easy to move those few electrons right at the edge of the move the atoms at the edge of the dislocation. So you can have strong bonds, but easy to move dislocations in metals. In ceramics, your ionic and covalent bonds are strong, but they also inhibit dislocation movement. So that's the big, big difference in mechanical properties of those two materials. And again, we did mention twinning as being a possible option, an alternative for deformation in addition to dislocation movement. And of course, in the case of most ionic and covalent bonds, even twinning is not available because again, you're bringing right into association with one another. Or again, it is simply restricted by the need for the hybrid orbitals and bond angles to be at a certain angle relative to one another. So again, the more at the atomic and microstructural level you are restricting movement, the less likely you can get plastic deformation, the less ductile, the less fracture tough. So there's ceramics in a nutshell, why they're brittle. Okay, polymers. This is polymers. If you stress them quickly, non-time dependent behavior. Quite a bit of the time polymers will undergo deformation viscoelastically, meaning they will have a time-dependent deformation in response to stress. Everything up till now, we've assumed that we apply a stress and we get a strain, elastic or plastic, and for the most part it doesn't really matter how quickly we apply the stress, how long we leave the load. With polymers, even at room temperature, we see that the rate of loading and the duration of loading will actually change the stress strain behavior, and that is the foundation of viscoelastic mechanical behavior. And we will pick that up in the next lecture, but be told that polymers can display at zero time, even non-viscoelastically, they can display most of the behaviors of the full range of metals and ceramics, plus some properties that are unique to elastomers, which are unique to the polymer category. So if you look at the red line, that's a brittle polymer. So that would be something like a fully cross-linked epoxy with no tougheners. It's going to behave almost like a ceramic. All of its deformation is going to be elastic, no yield, breaks, very little strain, very little area under the curve. Very strong, so high force, no displacement. Typical plastic that has some plasticizers. It's not a thermoset, for instance, basically maybe a thermoplastic with a few plasticizers, not very brittle, but not an elastomer, would follow the blue line. So this looks a lot like a metal, except for the fact that it doesn't have the characteristic maximum point in the stress strain curve, in the engineering stress strain curve, and that's because it doesn't undergo necking quite the same way a metal does. Basically the entire gauge length necks at once, and so you don't get that maximum that you do in metals. You actually get a dip and a rise again. And we will go over that specifically a little bit with an exercise in polymer behavior, one of your class exercises, I believe. Elastomers, again, behave sort of like the last portion of your thermoplastic, plasticized, your blue curve, your non-brittle polymers. You'll have very large strains, low stresses, and then the stress rising only at the very end, right before failure. And that's usually due to chain alignment. Elastomers tend to coil around one another in a fairly regular pattern. So when you're uncoiling, you can get tremendous deformations with very little stress. But as you begin to align those chains such that you're now stretching and pulling them apart rather than simply unkinking them, they'll start to pull back quite a bit harder at those larger strains, and then we see the stress rising. So that's why the slope of that curve starts to, on the elastomer green curve, rises so much more between strain 5 and 7 versus, say, between 2 and 3. So we will call it a halt for this lecture here, and we will dive into viscoelasticity and then safety factors in the next lecture. And just as a preview, viscoelastic behavior, we're going to center mostly on polymers, but every material category can display viscoelastic behavior under the right conditions. Particularly, we started our lecture discussing metals specifically below 1/3 of the melt point. So if we get above 1/3 of the melting point, metals will start to display these same kind of characteristics. So it's just a difference in temperature relative to melt or glass transition for the particular material. So we will see that next time, and see you then.